Okay, this video is about collection types in Python with brief asides for labels and laziness. So the basic collection types of Python are the list, which is similar to an array in a lot of languages, but has variable length and does not have to have homogeneous type. A tuple, which is like a list but immutable. A dict, which is like a hash table or associative array in other languages. It's short for dictionary. A set, which is, of course, from set theory. You can put things into it. You can get things back out, and you can take their length. A frozen set, which is an immutable set. And a file, which is a sequence of bytes or characters, often on disk, but not exclusively on disk. Here are some example list literals. The elements of the list are separated by commas. Here are some other ways of getting a list. Range, we'll talk about laziness in a bit, but range returns a lazy list from 0 to 2 in this case with range 3. If you want to make it eager, if you want to convert it to a list right away, you just apply the list constructor. And range 5, 10 goes from 5, 6, 7, 8 to 9. And again, you're converting it from lazy to eager using the list constructor. Here's some example list operators. You can slice. We'll talk about slicing some more. You can sort using the rather awesome timsort. You can concatenate two lists. You can append to a list, and you can extend a list with another, which is different from appending. Extending is essentially like appending 5, then 6, then 7. A list is a collection of potentially many values kept in order, indexed by whole numbers from 0 to the number of values in the list minus 1. They're similar to arrays, but they can grow and shrink. And as I already mentioned, they do not have to have homogeneous type. Deleting from or inserting at the end of a list is quick. The same operations, deleting or inserting near the beginning of a list, is slow for large lists. For small lists, it's fine, but for large lists, it's not good. Here are some more list operators. You can index them. This will get the fifth element of the list underscore. You can slice them. List of : 2 will give you every other element of a list, much like strings. And we already talked about appending. This example deletes the fifth element from a list. List.pop gives the last element of a list. It's convenient for using a list like a stack. You can use comparison operators on lists, like less than, equal, or greater equal, and the others. And you can take the length of a list with the len function. This comes up a lot in languages with immutable string types. Sometimes concatenating a string with another string again and again and again is quadratic. It really depends on which implementation of Python you're on, but it's best to assume that it will be. It's much faster to put all of your strings into a list and then join them, as in the second example here. That's guaranteed to be O of n. And when I say quadratic, of course, I mean O of n squared. Python, you can stretch it to say that Python has variables, but technically they're labels. Labels, unlike variables, do not have type. Values have type. Labels do not have type in Python. So you can say x equals 5, you can say x equals true, x equals 2.7. and x equals quote ABC quote, all in the same program, all in the same callable, without having any sort of type conflict. You're just changing the type of the value and the value itself that is associated with the label x. One good way to think of a label is as a sticky label you can put on a value. They just point a name at a value, and behind the scenes they're a bit like a read-only pointer. Unlike in mathematics, but like most programming languages, a label, once assigned, does not necessarily retain that value association forever. A subsequent assignment to the same label changes what value it is associated with, and possibly its type as well, as we already discussed. Though changing the type can perplex static analyzers in Python, like pylint. So it's actually better for reliability not to change the type of a variable within the same callable very much, so that your static analyzer can do its job maximally. Example of changing the value a label is associated with here. We're going to set x to a short list containing just 1, 2, and 3. Then we associate a second label with that same list. Then we replace the second element of the label of list x. And when we print x, we get back 1, ABC, 3. And if we print y, we also get 1, ABC, and 3, because y and x are associated with the same list. Python has something called an array. They aren't used much. They aren't nearly as flexible as Python lists, but they are faster, and they only contain scalar values, and they tend to be more compact. They're not used because they're just not as flexible. If you want an array of doubles, you use array.array of quote d quote and then a list to initialize it. Again, they don't see much use, but they are a decent reason to avoid referring to lists in Python as arrays. An important thing about arrays is that they use consecutive memory locations, so you can only put scalar types in them. Because if you had an array of references to values, it would no longer be much faster. It'd be almost the same thing as a less flexible array. I'm sorry, a less flexible list. So there's not much point. Some brief notes about tuples. Tuples are lists, except they're immutable, and their literals use left paren and right paren, not left square bracket, right square bracket. The main exception is that a tuple with a single element is written with left paren 1 comma right paren. Otherwise, it would just be a parenthesized expression if you left out that single comma, just for example. And it's unfortunately easy to accidentally end up with a tuple by writing x equals 1 comma. It looks pretty close to x equals 1 period, which would be putting a float in x. This is actually putting a tuple containing just one, just a single element in x, or associating x with that value. You can change a thing referred to by a tuple. It's just the tuple itself that is immutable. So if you have a tuple that contains a list, you can change what's inside that list, but you can't repoint the tuple at a different list, not without reconstructing the entire tuple. Here's our aside for laziness. Python is not a lazy language. Haskell is a lazy language, which is wonderful theoretically, but kind of hard to reason about. Python, on the other hand, has laziness in the places where you're most likely to want laziness and is easier to reason about than a fully lazy language. Here are some examples of laziness. We already touched on range being lazy. This range will return a lazy iterator from 0 to 999,999, and it returns them one at a time. It does not build an entire list and then return it en masse. It does not build the entire result before beginning to produce usable values. If you do want eager evaluation, again, you can pass that iterator into the list constructor. Dictionaries are a little bit like a real-world dictionary on your bookshelf, but they're not sorted. There the analogy ends. Again, they're a bit like a hash table or map or associative array. And they're a collection of potentially many values that facilitate easily finding where you put something previously. So it does O of 1 amortized insertion and deletion. Here are some examples of dictionary literals. The empty dictionary is just left curly brace, right curly brace. Here's a 2-element dictionary where A is what you use to look something up by, and ABC is the value associated with A. B is the value you can look things up by, and BCD is associated with B. And you can also have non-homogeneous. You can have heterogeneous types in dictionaries. Here's another example of using a dictionary. We create an empty dictionary D, then we put powers of 2 in that dictionary, and then we can actually say D of quote X quote equals 1 of the powers of 2. If we print D of 0, we get back 1, and if we print D of X, we get back 16. Further operations on dictionaries. Much like a list, you can use the len function to get the number of key value pairs in a dictionary. You can merge 2 dictionaries with update. So D1 ends up after this call with all the key value pairs from D1 and the key value pairs with D2, where any duplicates between the keys in D1 and D2 are overwritten with the keys from D2. List of dict returns just a list of keys. You can also say just for key in dict colon. We'll get to control flow in a while, but you can also just do an iteration over just the keys of a dict with a simple for loop. You don't necessarily have to get back a list of keys. You can get a lazy iterator of the keys. You can also use dict.values to get all of the value part of the key value pairs within a dictionary, and you can use dict.items to get back an iterator of key value tuples. So they're 2-element tuples that contain the keys and values. And you can test dictionaries with equals equals and bang equals for equality and inequality respectively. As we already touched on, dicts like to return iterators, and you can convert an iterator to a list. There are some restrictions on what you can use as a dictionary key. Dictionary keys must be immutable values. They must support hashing with Dunder Hash, and they must support equality testing with Dunder EQ. You cannot index a dictionary by a list or another dict, but you can index a dictionary by a tuple or a frozen set, because the former are mutable and the latter are immutable. So again, you can index a dictionary by an immutable type, but not by a mutable type. And you can put pretty much anything you want into a dictionary as a value. It's only the keys that are restricted. Sets, again, are like sets from set theory in mathematics. From Wikipedia, a set is a collection of distinct objects considered as an object in its own right. Sets are one of the most fundamental concepts in mathematics. Sets compared to dictionaries. Sets are a lot like dictionaries minus the values. All they have is the keys. There are no key value pairs in sets. The restrictions on set elements are the same as for dictionary keys. And a little historical note, Python hasn't always had sets, and in the old days, dictionaries were so much like sets before sets existed that we would just use a dictionary with values of all zeros or all empty strings or something and fake having a set that way. So they're really quite similar. It's just sets are a little cleaner. Creating a set. Here is a set literal with just A, B, C in it. And an empty set is created with set left paren right paren because, of course, empty left paren right paren is already used by dicts, so we needed something else for sets. Example set operations. You can take the cardinality of a set, that is, find the number of members in a set with len, just like for lists and dictionaries. You can find the intersection of two sets with the ampersand. You can find the union of two sets with a vertical bar. You can do a difference between two sets with S1 minus S2. And you can do membership testing with the in operator. You can compare two sets nicely. No surprises there, really. A frozen set is just a set that you can't change, an immutable set. And to create a frozen set, the syntax is not quite as pretty, but it gets you where you need to go. You pass a list to the frozen set constructor. Backing up a sec, pretty sure you can also pass an iterator to the frozen set constructor. And moving on, almost done with the video. For files, a file is a sequence of characters or a sequence of bytes, usually thought of as being a file system in a file system on disk. But Python has things called file-like objects, which can impersonate files. One common use is to have a file that exists only in memory. Another is to have a file that builds a file-like presentation to the caller that generates data dynamically. Some examples of files, of course, .ods or .xlsx files in a file system are files. A text file usually ends with .txt. A Python file ends with .py. These are files within a file system. They're different from the files that I'm about to talk about. sys.stdin, sys.stdout, and sys.stderror are, of course, like C's stdin, stdout, and stderror. They live in the sys module. You can also get back a file to read temp blah using the open constructor, and that R is quite similar to what you would see with fopen in C. And you can get a all in memory file-like object using io.stringio. Common file operations. Reading a file, you can get the first 10 characters of a file with read sub 10. This with statement is kind of fun. We'll talk about it more under control flow. But it says open that file and then run all of the commands that are indented under this with file in existence. And as soon as we dedent, that is, as soon as we stop indenting to that level or greater, we're going to close file automatically, so we don't have to remember to close files. And of course, align equals file.readline left right is going to return the first line of a file minus the first 10 characters, assuming there were no new lines in the first 10 characters. Anyway, it reads a line, and usually you don't combine read with readline. I just wanted to simplify the presentation a little bit. File operations on a file are lazy. So if we with open temp foo for reading as file, we can then say for line in file and print line, and that won't read the entire file all at once. It'll print the lines one at a time. Oh, and it'll print 2 new lines for each line this way. We could say print line end equals quote quote, and then we'd get just the new line from the for line in file we're getting for each line in the file of the text file. You can also write files. This is quite analogous. We're just using quote W quote instead of quote R quote. Reading binary data from a file. The easiest way to read binary data is to use quote RB quote, where the B stands for binary. And that's going to, the block that we read is going to be of type bytes. And a file-like object, you can read from that as well, and you can close it. You can also use with. But here we're just using close in this example. And again, we can assert that is instance data, bytes. That checks to make sure that data is bytes, and if not, raise an exception.